Set up. So our first speaker is Aleksandra. Okay, I'll give my best here. Is it Ciprijanovic? Is that close?
Really
okay.
Yeah.
Who's a Wilson Fellow at Fermilab in the Data Science Simulation and Learning Division, and I believe you're the co-lead of the Cosmic Group. Is that correct? And part of the NSF and Simon's AI Institute for the Sky, or SKAI. She works on AI for astrophysics and cosmology, big data and simulations and astronomical surveys. And so basically we'll open with some AI and astrophysics. So take it away.
Thank you so much. Thank you so much for inviting me. I'm very honored and happy to be the first one to present today. You can see the topic. It is about domain shift, model robustness, and even though my background is in astrophysics and currently most of the projects that I work on, but not all, are in some way connected to astrophysics, you will see that this problem is a very general one and very applicable to probably most of your projects. This topic is one of the topics that was covered during the summer school. You can see the 4 really cool topics. I think the school went absolutely brilliantly. So if you are an early career scientist and you have not been to the summer school, please reevaluate your choices and apply next year. Okay, obviously other 4 topics or how many topics they decide to have will be next year, but it is a really, really cool event. So I was very happy to be part of it this year as well. So for those who have been at the workshop, this is going to be in some way a very short recap of what we talked about in a lot more detail, but maybe with some other things to think about kind of in addition to that. So basically, I always like to start this discussion with a paragraph that was kind of I first saw it, at least in the context of astrophysics, in this really nice review paper that talks about the uses of AI in astronomical surveys and in astrophysics in general. And in this paper, authors mention a couple of different problems that people are currently facing whenever they want to use AI on an astro topic. So basically, the first problem, even though we definitely live in the big data era, whether that's astro or physics, that's absolutely true. But we do also lack really good, trustworthy labeled data sets. So often we will just have the data, but not the labels, or they will be questionable. So building models on such data sets is difficult, especially if you want to do supervised learning model. So this is the first problem that even many students with their first projects face. So what is the next step if you are facing this problem? Well, the next thing that you can think about is, well, maybe in that case, I can start not directly on the data from my experiment or from a telescope. I can start from a simulation. In simulation, I am in charge. I can make the simulation any way I like, and hence, I absolutely know what the true labels are. So it is very easy for us to create trustworthy labeled data sets from simulations. But if you use a simulation like that to train your model, you will notice that as soon as you move to your final real data set where you want to apply your model to, the performance will often drop and sometimes, sadly, drop catastrophically. So you will be very frustrated, and then you will try to understand why the model failed and better understand the uncertainties around your predictions. And if you start diving deeper into this topic and start looking at papers, whether those are like pure like CS papers in this area or any of the applications, you will realize that this area has many unanswered questions yet. And even the terminology of what different error bars mean can be very different in different papers. So this is a very problematic area, gray area still, that we really still need to improve. The next thing that you might ask, well, if my model is making mistakes, why is it making these errors? And then you might want to try to interpret your model But again, if you start thinking a little bit more deeply about this problem, you will understand that, again, the interpretability of our models is not where we want it to be. Yes, you have some methods to maybe look at your gradients or activations or just in the latent space of the model. But what you're concluding from that is very tricky and questionable. And then as a last resort, you can ask, well, can I at least compare to my peers? Can I compare my model to the other people that work in this field? And in many cases, the answer is no, or the comparison will take a lot of time and it will not be very easy to do. Because compared to regular, like pure computer science AI papers, where people often will have a lot of benchmark data sets, they will put a table in there and compare their models to all the other people who are doing similar things and then compare whose model is doing better. In astronomy and in physics, it's not as very easy. We don't create like public benchmark data sets. And if you want to redo your analysis with somebody else's model, maybe you need to do the whole data pre-processing. Maybe the data isn't even available because it is not publicly available outside of that collaboration. There are many obstacles, basically. So even if you wanted to make a table like that, you might be able to add a few lines in there, or in some cases, even none. Or you would just need a lot more time to actually make the table. So basically, I think likely you've kind of recognized yourself, at least in some of these problems, if not all. Many times, all of these. But my plan today is to basically mostly talk about the domain shift problem and then kind of touch upon the uncertainty estimation and interpretability kind of in that context as well, because they are, in some sense, not really separable. So this is kind of the outline of what we're going to talk about. I want to expand a little bit on this domain shift problem, what it is. Then I want to tell you how we can solve it in many cases, but maybe not all. Then I'm going to talk a little bit about UQ, and then ultimately, in the end, I want to show you just a few example projects, just to kind of demonstrate where we can use it and maybe inspire you to use that as well. Okay, so what is domain shift problem? So, as I said, in cases where you want to build a model that can work across multiple data sets, for example, you might have a simulated, if you're an astro person, you would use a simulated data set, for example, of galaxies from Illustris. This is one of our famous cosmological simulations. And then you might have your observational data set. If you're a neutrino person, you might have, I don't know, a microboon detector simulation. This is one of the detectors at Fermilab, and then you might have an actual data point from event from actual running of the experiment. But even if the differences between these are not as obvious as you can see here, even if they're very small and maybe sometimes not even kind of visible to us, there are many differences. They can come from either imperfect simulations, whether that's because we don't know the whole physics, or maybe the way the current understanding of physics is not good enough. Maybe we're not adding background levels good enough. There could be all kinds of reasons why the simulation is imperfect. And of course, many of our simulations are extremely complicated, so often we need to add a lot of approximations. We need to add all kinds of recipes to make them run faster, and this ultimately leads to, again, differences compared to the real data. You can also have detector problems. So you can have differences that are kind of on the side of real data. Maybe you have some problems with your detector. Maybe you have huge data sets, so you have to move it around. You have to compress it and decompress it. Even that causes sometimes differences in data. Maybe your addition of for example, in astronomy, we add observational noise and blurring by the telescope. Maybe that's not perfect. Very likely it isn't, especially if you're trying to mimic ground-based observations. So all of these things can cause problems. And here I'm also pointing out that maybe you're not even, in cases where you're not working with simulated and real data, maybe you have your old experiment and new experiment, or old survey and new survey. In that case, all of the properties of the data is going to be different, whether that's pixel scale, if you're working with images, noise levels, and so on. So all of these things cause problems to machine learning models. So let's describe an example of very simple regular training of a CNN and how we would classically, like standard, do it. So for example, I could get these galaxy images from this illustrative simulation that I was mentioning, and I have labels. And let's assume that I'm extracting merging galaxies and regular non-merging galaxies. And I really just want to do a very simple task of classifying these two classes. I train my CNN. The CNN extracts some useful features, and actually this is a grad cam showing which pixels the model decided are the important ones in this particular case, and the model decided that it's very, very useful to look at the periphery of these galaxies, and if it sees some like asymmetric clumpy information, that could be a sign of a merger. So the model is then ready to classify these two classes. And if I show it the test set, the holdout set from the simulation, it works just fine. But if I want to pretend that this is actually a real observation, and I add observational noise, for example, mimicking Sloan Digital Sky Survey, I will have something like this. And the model will fail absolutely miserably. And it makes sense, right? So the model decided to look at the periphery. The periphery has no useful information anymore. So the model will obviously fail. So internally, what happens, right? The model learned which features represent class 1 and class 2. It moved them to different areas of the latent space. It decided what the decision boundary between the two classes is, supposed to be. And then once we'll forward the different looking image, those trained filters do not kind of translate that image into the internal latent representation of the model in a correct way. So all of a sudden, right, you have a different decision boundary that's not aligned with the one that you learned, and obviously you're going to make a lot of mistakes because of that. So basically, the idea of all of these domain adaptation methods that I'm going to talk about today is basically how to perform domain alignment, how to put the correct class on top of the correct class, so that we can basically have a common decision boundary and a model that can actually work on both data sets. So, as I said, now I want to talk about methods to solve this. So basically the whole logic behind, as I said, these are called domain adaptation methods. The logic behind them is to try to modify the training procedure in some way. There's a plethora of different ways to enable the model to learn domain invariant features, so features that are present in both data sets. If we learn such features, the model will see the data set similarly, and all the classes, if we're doing classification, will be properly aligned. The main reason why we might need to use such a method is, in many cases, the target data set, the one that we ultimately want to use our model on, is very often, as I said, unlabeled or has very few labels, or they're very not trustworthy. So you can't just directly train on it. You can't do transfer learning. And in that cases, you can use domain adaptation. And this is really great because it allows you to build a model on the new data as soon as you get it. You don't need scientists to label everything. And while this whole area of research is really broad, I will just mention 3 different approaches just to kind of paint a picture of how completely different ideas lead to the same result. So there is a very large group of methods that are based on measuring a distance between these latent distributions, or distance-based methods. And this is just an example that I'm putting here, which is called maximum mean discrepancy, but you can decide on whatever distance measure you want. And if you add that distance metric as your loss function, as additional loss function, and you try to minimize it, what will happen is that the latent representation will slowly drift together towards each other, and they will align. So this is one kind of approach. The other 2 types that I'm listing here are basically using some kind of auxiliary task to get to the same result. So this auxiliary task here, adversarial methods, instead of having a regular neural network, like for example for our merging non-merging classifier, we would have convolutional layers and dense layers that classify the classes. We add an extra branch that's actually classifying the domains. So in this case, the pink branch only sees class simulation and class real data, and it's trying to distinguish these two, and we are actually trying to fool it. So there is a gradient reversal here, so we are trying to make this branch not work. So what ends up happening is that filters here are extracting information that are useful for classification of merging galaxies, but useless for classification of the domains. Hence, domain invariant features. They have to be present in both data sets, and they have to still be useful to figure out if something is a galaxy that's merging or not merging. The last part is similar. You still have two branches, but this extra branch is doing data reconstruction. So your real data would go in here, and then from the latent space, you need to be able to reconstruct it. Slightly different approach, but the result is ultimately very similar. So practically, what do we do? How do we modify the training procedure? So now, instead of simulated images with label, at the same time, we have another data loader loading observed images without labels, because we are saying that there are no labels in this data set. Because of the domain adaptation loss, whichever you want to do, the features from any feature kind of change into domain invariant features. So in this case, from looking at the periphery, instead of doing that, the model starts looking at the center of the galaxy. And in this case, the center is the only one that survives after you add the noise, so this is where the model should be looking at. So in the testing phase, you can have a test set both from simulation and from real data, and the model will work just fine. So let me show you how that actually looks like internally in the model. So here I'm plotting just the TS&E 2D representation of the latent space. Just so that I can convince you that things do move closer to one another. So in this case, this is before any training has started. So I have two classes, again, merging and non-merging. Source domain, labeled data, is this illustrious simulation. The target data are real SDSS observations, and I'm pretending that there are no labels. So there are no labels being used from this side. In both cases, like the red and blue ellipse are kind of showing where the data sets are lying. And both of them are mixed, right? No training has started. So if I just train on the source, like regular training, no domain adaptation, just these data and the labels, this is how the latent space ends up looking. So the source domain, or the simulated images, start being kind of differentiated. You have a kind of blue area and red area. And accuracy ends up being slightly over 80%, which for this problem is really good. So this is not MNIST. But the target data set is still mixed. So these real images are lying here. They're mixed. Model is basically randomly guessing the class. So if I now modify to use domain adaptation of my choice, I get this. So all of a sudden, we really do have red area and blue area, and both data sets are aligned correctly, and the accuracy here jumps from like 50 to 80%. So it's almost as good as the source. And depending what kind of problem you might have, you will have different kind of performance in source and target, but overall, very often you can dramatically increase accuracy in the target, which is really good. But I have mostly talked about this simple example of a CNN classifying something. But in general, you can use it on any kind of task and more or less any kind of model. So depending on if I have one or maybe multiple source domains, and I have my final target domain where I want to apply the model to, I can use all of that, and I will just choose the appropriate encoder. If I have images, I'll use a CNN. I might have time series, and then I have to use recurrent neural networks or a graph neural network for big graph data or big tabular data sets. Ultimately, you use whatever you need to summarize these complex data sets into something simpler, into the latent space. And then in the latent space, you would plug in your domain adaptation method of choice. And then, again, choose the appropriate decoder for a task. So if you're classifying or doing a regression, you can just have a few dense layers and have your output out. But you can also do anomaly detection, data generation, whatever you want. The whole goal is that this task can now be performed from the aligned latent space and can be actually performed well on both data sets, or all of the data sets that you're using. But I do want to emphasize that while, yes, we can do this in many cases, the error bars, so the uncertainty quantification and the interpretability of these methods as all other methods. This is not a problem just reserved for domain adaptation. It is, in general, not where we want it to be. So, I mean, it would be really good if, like, for example, interpretability was way better than what we can do now. So if we could truly interpret model behavior, we can maybe even say and understand which features the model is using, which features disappear when you add domain adaptation. And it can hopefully maybe even in the future point us towards like the physics in the data, the physics that is kind of domain invariant versus things that are maybe model dependent or detector dependent, things like that. And so with that being said, I do want to kind of just have a minute or two talking about uncertainty quantification in general, just because while it is a problem everywhere, it is an extremely big problem in domain adaptation, I would say, in some cases. So to talk about this, let me envision this simulator that you want, for example, I want to use, and it can be whatever simulation you would use for your research. How would you do it? So you would choose your physics parameters, your thetas, with some prior ranges that would go into that simulator. The simulator can be super complicated, even have some internal parameter z that you might not be able to fully track. But ultimately what you want are the data points x. And so we could then train some kind of neural network to connect x with theta so that we can, for example, predict theta parameters from the observables from x. And initially, we were really, really, really happy, even with deterministic models, with just predicting a point prediction for the theta. Because at least these deep learning models allowed us to do these regression or inference very, very quickly. And if once you train a model once, you can just apply it to your data, and everything is great. After that, we realized that we still do want some kind of error bar, at least in science. So we build models that can predict kind of a mu and sigma for all of the parameters. So we're pretending that we are predicting Gaussians and that this is a good approximation for whatever we're predicting. Obviously, we know that that's not true in many cases. So in last, I don't know, couple of years, maybe a little bit longer, we started using normalizing flows and simulation-based inference to enable us to build kind of posteriors of arbitrary shapes so that if we think that this is not a good approximation for the thing that we're inferring, we can actually get something that is more like what we expect, or if there are correlations between parameters, if you're inferring more of them, you should be able to see this. But what is the next step in UQ? Because ultimately, there's still quite a lot of unanswered questions of how errors from the data and the model propagate to these predictions and so on. So while, yes, I do hope that people will come up with even better deep learning models and even better error estimators, there are things that we can do right now, even while waiting for somebody to give us better methods. And that is to align intent and implementation of uncertainty quantification methods to our models. And I'm actually just quoting this paper from my group, which I really do recommend you to read if you're interested in this topic. It's a position paper, and they're basically advocating for epistemic hygiene, meaning they have a way longer list in the paper. But for example, what they mean by epistemic hygiene is you need to clearly declare what you're doing, what is the purpose of your paper when you're you're submitting to a journal. So what is it that you want to do? What kind of method you're choosing? What kind of AI model? And then match the uncertainty quantification method to that context, because different types of tests are appropriate for different types of problems. You also need to kind of check whether your model has both forward and inverse validity, whether everything holds up in both the data and the kind of latent parameter space. And if you have a simulator, then you should use it not just to get the result, but also as an instrument to test when the model will break. So you can perturb different parameters in your simulator if you're lucky that you have a simulator that doesn't run for 2 months. So if you are lucky like that, you should use it. Because you can kind of add errors to different parameters of your model and see what happens at the output. And then you can really understand what's going on. Especially when you're benchmarking, you can also benchmark outside of IID samples if you have a simulator. Because that is also what you'll have when you go to real data, when you move to a different data set. You can also use it to just test model stability, meaning what happens if I do a different random seed or a different realization of my data set, and so on. There are many things you can perturb. Why am I mentioning this in kind of the context of domain adaptation? Well, because most methods, if you just blindly use them, even if you have a Bayesian neural network or something, and you are predicting some kind of error bar, you are assuming that your samples are kind of IID. But if you're dealing with a domain shift problem and you are planning to apply the model to a different data set, very often that's not going to hold, like this assumption. So basically, you will have a model, you have chosen a model that predicts some kind of error bar, but the error bar can be completely meaningless and you won't know what's going on. So very often, you can get a very overconfident model that is still predicting error bars that are too narrow. And if you, for example, really don't have labels, you are truly trying to do prediction on a new data set without any labels, there's no way for you to know what's going on. So very often you'll have like confidence in accuracy of your models in the out of distribution data set is going to be kind of all messed up. And the model error, epistemic error will be dominating in many cases. So sometimes, yes, you do see once you move to the target data set that your error bars will kind of inflate. I'll show you an example of that. But they will very likely not inflate enough, so you will still get a very overconfident model. And again, as I said, in real applications, in many cases, you just don't have a way to actually evaluate it. And with that, I just want to go to show you like 3 example projects, just to kind of illustrate what I was talking about. So in this project, several undergraduate students were asking the question, can we infer strong lensing parameters like Einstein radius, ellipticity, position offset robustly in both the simulated data and here we're making mocks of dark energy survey. So we're pretending that this is real data. So for those who are not astro, strong lensing happens right when you have 2 galaxies on the same line of sight. And the one that's closer to you, the mass of this closer galaxy is bending the light from the object that's behind. And instead of seeing like a normal looking galaxy, you basically see an arc or parts of an arc. So depending on the masses of the objects and their brightnesses and also their position and shapes, you will have a slightly different looking ring or an arc. So basically, the physics of like how light bends is pretty simple. So in theory, once we have the image, we should be able to infer the properties of these objects. So these are our 2 data sets. We're pretending that we have labels for the clean one, and we are pretending that we don't have labels for the noisy one, just so that we can evaluate. We, of course, have labels. So if there's no domain adaptation, this is how the latent space would look like. So here, the color of these points is actually the value of the Einstein radius theta. So it's one of the parameters that we're inferring. So while there is a kind of a similar gradient direction, they are detached. But with domain adaptation, we were able to fully align them and then just have a single gradient in color for this parameter, meaning in both data sets, the theta parameter changes the same way when you move around in the latent space. And let me show you how kind of predictions improve. So this would be kind of a quarter plot of residuals. So for the entire test set that we're applying this to, we are looking at the difference between the true value and the predicted value, or like the maximum likelihood version of the prediction. And we're just looking how different they are, right? So if we have very few errors, these distributions should be centered in 0 and very narrow. And for the clean, the source domain, we are looking at the pink curves, and you can see all the pink ones are very, very tiny and very nicely centered at 0, 0. The noisy data set, the target data set, if there's no domain adaptation, blows up to these orange curves that are way bigger. Luckily, we don't have any systematic offset. They're still at 0, 0, but they're much bigger. But if you do use domain adaptation, you can shrink that to these blue curves, which are pretty good. They're almost as good as for the clean images. And I mean, obviously, there's way less information here with the noise, so we're pretty happy with that. I didn't put here, but when you actually look at the confidence of the model, the orange model was actually overconfident. So even these errors are not good enough. They're too small. Yes, so this is one such project. This project was using simulation-based inference and normalizing flows, just so we can get a nice posterior out of all the predictions. Okay, here's another project, a completely different one in some sense. Well, it's still kind of cosmology related. So in this case, a summer student who visited Fermilab was asking the question, can we correctly predict cosmology across different cosmological simulations? So in these are 4 different cosmological simulations: Illustris, Simba, Astrid, and Magneticum. All of them are run by different groups. They all had their own internal decisions how to do different kinds of approximations and especially how to add small-scale astrophysics, which we know less about, to the code. And if you run these simulations with the same kind of initial conditions, the same random initial seed where particles are, you will end up with a different evolution. You can see kind of roughly the structures are the same place, but the brightness of different areas is very different. So I think the blobs are kind of gas temperature, and these are getting way hotter than these two here. So if we try to infer cosmology, so infer these cosmological parameters from any of these and try to apply it to any other, we will fail. And obviously, that means that we will likely also fail on the real data because none of these are good enough. I mean, there's no way that one is miraculously absolutely correct and all the other ones are incorrect. So let me show you how that actually looks like. So in this case, this was just initial proof of concept kind of summer project, so there's still a lot of work to do. But what we were doing is we were using graph neural networks to encode the whole box from the simulation, and then use the graph neural network to summarize it into some kind of latent space where we can plug in domain adaptation of our choice. And then hopefully we were initially just wanting to see if we can just cross between the two simulations. For example, Simba and Illustris. And ultimately, hopefully, I mean, if we can do this at scale and better, maybe sometime in the future we can actually safely use it on real data. So let's look at the top row here. If I train and test on the same simulation, so in this case, train and test on Simba, all the predictions are here at this red line where I want them to be. So this is true and predicted values. If I train on Simba but test on Illustris, I get this. So I'm obviously offset. And if you look at the latent space of that model without domain adaptation, you can see why this happens. So the solid ellipse is kind of around the source domain, around the Simba simulation, and you see that there is a nice gradient because we're training on this data set. But the Illustris is here, completely messed up and on the side. So obviously there's no single uniform gradient. We can't expect it to work very well. But with just the first thing that we tried, basically you can still see already that some of the points are starting to move up, and the latent space was much better. There is basically a single gradient. In theory, there are circles and triangles here, but very tiny, so you can't see them. But in general, yes, there is a single gradient. The errors were much better. But again, this is just literally the first thing we tried. That being said, obviously there's still a lot of room to improve. And this is because as soon as you kind of include a second loss function, like this domain adaptation function, you already have to start thinking about how to balance the two losses. And so in all domain or not domain adaptation projects where you have multiple losses, you need to find the best way how to kind of balance them so for like best performance. And in this case, we didn't have time for hyperparameter tuning, so this is kind of the last plot that I can show you. And with that, I just want to announce another project where we were asking the question, or Sneh was asking the question, he's here, can we perform automated domain alignment so that we don't have to do this very time-consuming and very painful hyperparameter tuning? And well, the answer is yes, and I will just flash this figure and not tell you anything about it because I want you to go to his talk on Wednesday and actually hear all the details. So this is just the announcement of, yes, you can do domain adaptation without it being actually painful. And I'm very happy that he showed us that we can do this. Well, okay, with that, I do want to leave you with this kind of circle of doom of all the problems that we are still facing, and just tell you and remind you that even though we are in the big data era in physics and in astro in general, in many cases, you do not also have a very good large labeled data set, and hence, many cases you will need to use domain adaptation. There are many other applications beyond that where domain adaptation can add kind of robustness and make your model more stable in many other cases. If you want to talk about that, please, I'm around. But yeah, as I said, interpretability and understanding error bars of our models is nowhere near where we want it to be. So hopefully in the kind of next decade, we will get that all sorted out and we will all just be happy. Thank you.
Thank you. All right, do we have any quick questions for Aleksandra?
So at some point you mentioned extracting the most important features or pixels. Do you use some sort of saliency map for this, or how do you extract those?
So we mostly ended up using GradCams, which are like those blue cutouts that I was showing next to because I don't know, they seem, because they're kind of blurred and blobby, they're a little bit easier to look at. Where are they? These things. Yes. So this, you can think of them as saliency maps, but the saliency maps are, in some sense, a little bit more detailed, but also very hard to look at least the way I found it to be. So like I prefer these, but yes, we mostly look at that and the latent space, whatever dimensionality reduction you can use. Yeah.
Thanks a lot. Very nice. I had two questions. Mm-hmm. First of all, how do you deal with like mode collapse on this like new classifier? For example, the GANs.
So in general, like if you would do something like a GAN, you can use the same type of approaches that like modern architectures do. In most cases, I have not used anything that's at least so far, I didn't need to do data reconstruction. So I didn't really have a lot of those problems. In general, I mostly use either distance-based methods where I'm just kind of trying to move the whole distribution around, or class-aware where I want individual classes to move around. But you are right that if you would blindly use something like a GAN, you could like just easily get mode collapse. So yeah, I mean, I don't have any specific solution for you, but in general, yeah, you would approach it as with regular GANs to solve it. Or I mean, if you see that you have such a problem, you have honestly a plethora of different methods, so you could try something else basically. But yeah.
Thanks. And the second one is, how does like a traditional domain adaptation approach compared to like clipping or like contrastive learning on the latent space do?
So the good thing about, I mean, in clip models, right, you have to have exact kind of pairs so that you can kind of make that matrix and compare everything to everything. But in general, in domain adaptation methods, you have a lot of them that don't really, they're not so like kind of rigorous. You don't have to have exact examples and pairs from both data sets. And in that sense, they're more flexible and also kind of faster to train. And plus, you don't have to, okay, depends on the problem, but in many cases, you have applications where you don't have to do like, oh, I'm pre-training this encoder and that encoder, and then I'm trying to align them. You basically just have a single training procedure. You just forward everything to the model, and then do, during training, some kind of alignment. It can even sometimes be self-supervised. If you really want to be super flexible and don't want to think about the shape of your distribution and whether, for example, in one data set you have a very numerous class, but in a different data set you have like only few examples. Like the data distribution is very different. There are also methods that kind of focus on flexibility, so that even if you have fewer samples here, you can still move them around and put them closer to the other. But so in general, I would say that they are more flexible. That being said, of course, if you have like good overlap and you have exact samples from both data sets, that's great, you can use that. But in general, in many cases, it's easier even to do, I think, than, yeah.
Thanks so much.
Hi, thank you for the talk. So one of the things that I was thinking about, I guess, as like specifically for this slide and this kind of example that you gave, as you're, I suppose, like training the model to find features that are more present in both the simulation and in like the observed images, have there been examples where you've maybe like learned more about how to like adjust your simulations from this, seeing that there are like features that are more present in like observed images than there are in like the simulations, and maybe, you know, kind of adjust the simulation side of it to make them more accurate from there?
If I understand, let me see if I understood your
Sorry.
question correctly. So are you asking if we could find the features, so using domain adaptation to make the simulation even better?
Yeah, essentially.
I think, so this is a great question, because this is what I would love to happen in the future. I think at the moment, as I said, the interpretability is kind of tricky, but if we could really trust what we are like kind of interpreting as what the model picked up, then we can say, okay, this is the biggest cause of the difference between the two simulations, let's improve that part. And then we have a smaller gap.
Right.
We're not there, but I hope
sense.
we will be.
That was actually my question I was going to ask as the chair, was actually, okay, could you reverse engineer this and actually like feed it back into the...
That's what I write in all of my proposals.
Okay. But then you don't want to do it because then you won't be able to get any money in the future, right?
Yeah,
if you actually
I
succeed
have to do it very slowly.
All right. Yeah. All right, well, we're out of time, so let's thank Aleksandra.
Thank you.